Imagine staring at a blank screen and watching words appear, driven by nothing more than your silent intention. No keyboard, no voice commands, just the raw electrical symphony of your mind translating directly into digital text. This is not a scene from a distant science fiction future, but a reality unfolding right now in research laboratories around the world. We are standing at the precipice of a monumental shift in human evolution, forging a direct link between our biological wetware and the silicon architecture of the digital realm. At the heart of this transformation are brain-computer interfaces, or BCIs. These systems act as a profound binary bridge, translating the analog pulses of human thought into the digital language of machines. Every time you move a muscle, recall a memory, or form a sentence, your brain generates a storm of electrical activity as billions of neurons fire in complex patterns. By placing delicate sensors near these firing cells, neuroscience researchers can eavesdrop on this electrical chatter, capturing the literal sparks of human consciousness before they ever translate into physical action. The journey to unlock this neural code began decades ago with rudimentary experiments where researchers first realized that human intention could be mathematically isolated. In the late 20th century, scientists at institutions like Brown University began translating the motor cortex signals of paralyzed individuals, allowing them to move a digital cursor across a screen using only their thoughts. Those early, painstakingly slow movements proved a radical concept. The mind could, in fact, reach beyond the confines of the skull and manipulate the external world through direct connections. Today, the hardware bridging minds and machines has evolved from bulky external wires to sophisticated neural implants. One of the pioneering devices, known as the Utah array, resembles a tiny bed of microscopic nails, each tip resting near a specific group of neurons. When a patient imagines lifting an arm, the array captures the spike in electrical voltage. That raw data is then fed into a computer, where complex algorithms decode the specific intention, translating the biological command into a digital instruction for a robotic limb or a software program. The impact of these early devices on individual lives has been nothing short of miraculous. Consider the experience of a patient with severe spinal cord injuries, locked inside an immobile body for years, suddenly able to reach out and grasp a cup of coffee using a robotic arm controlled entirely by thought. The machine becomes a seamless extension of the self. The patient does not think about operating a robot. They simply think about moving their hand, and the binary bridge executes the command. But an unexpected phenomenon emerged as these direct neural connections became more sophisticated. The brain, highly adaptable and endlessly malleable, began to treat the robotic appendage as a natural part of the body. Through a process called neuroplasticity, the patient's neural networks physically rewired themselves to optimize control over the machine. The biological system and the artificial hardware were not just communicating, they were actively learning from one another, blurring the lines between where the human ended and the machine began. Building on those foundational discoveries, the current frontier is dominated by high-bandwidth systems designed to capture vastly more data. Companies like Neuralink are developing ultra-thin, flexible threads inserted into the brain by surgical robots with microscopic precision. These advanced neural implants are designed to read thousands of neurons simultaneously, promising a level of thought control that is incredibly fluid and precise. The goal is no longer just restoring basic movement, but creating a high-speed data connection between the human cortex and artificial intelligence. While surgical implants offer the highest resolution for reading brain activity, a parallel track of research focuses on non-invasive methods. Wearable devices, like advanced electroencephalography or EEG caps, read the brain's electrical signals through the scalp. These external interfaces are safer and far more accessible, but they face a significant engineering challenge. The human skull acts as a thick insulator, muffling the delicate neural signals and making it difficult to decode complex thoughts with the same pinpoint accuracy as a direct implant. But what if the muffled signals of the non-invasive approach could be clarified by advanced software? The real challenge lies in the translation layer, and this is where machine learning enters the equation. By feeding massive data sets of brain activity into sophisticated artificial neural networks, researchers are training algorithms to find the hidden patterns in chaotic electrical noise. As these decoding algorithms grow smarter, the need for invasive surgery might diminish, opening the door for brain-computer interfaces to become a commonplace consumer technology. If the friction of physical input is removed, the implications for global industries are staggering. Imagine a world where architects manipulate three-dimensional models in virtual reality simply by visualizing the structures, or where software engineers write complex code at the speed of thought. The traditional bottlenecks of keyboards, mice, and touchscreens would vanish. This shift would fundamentally redefine productivity, transforming any profession that relies on digital interaction into an exercise of pure, unencumbered cognition. Yet, as we move closer to this reality, a profound ethical dilemma emerges from the shadows of innovation. If a machine can read your intentions before you physically act on them, what happens to the privacy of your inner life? The data being harvested by a neural implant is not just a record of your clicks or your search history. It is the raw, unfiltered stream of your consciousness. The very sanctuary of human thought, previously impenetrable, is now becoming a quantifiable, extractable resource. Furthermore, the algorithms decoding this data are not passive translators. They are predictive engines designed to anticipate what you want to do next. If an algorithm completes your thought or executes a command slightly before you consciously finalize the decision, who is actually in control? The subtle human oversight that usually governs our actions could be bypassed by a machine that knows us better than we know ourselves, raising complex questions about personal autonomy and free will in a hyper-connected age. The psychological weight of this intertwining is deeply complex. Individuals living with advanced neural implants often report a strange, shifting sense of identity. When a thought instantly triggers an action in a smart home system or a connected device, the boundary of the self expands outward into the environment. The digital infrastructure becomes a peripheral nervous system. This profound integration challenges our traditional understanding of individuality, as the mind learns to inhabit a network of machines just as naturally as it inhabits a biological body. To deepen this connection, scientists are now pioneering bidirectional interfaces. It is no longer enough for the brain to simply send commands to a machine. The machine must also speak back. Researchers at institutions like Johns Hopkins University have successfully programmed robotic limbs to send sensory feedback directly into the somatosensory cortex. When the robotic fingers grasp an object, electrical pulses stimulate the brain, creating the distinct physical sensation of pressure and texture. This closes the loop, transforming a mere tool into a true sensory organ. The patient does not just watch the robotic hand touch an object, they literally feel it. This bidirectional communication bridges the final gap in the human-machine relationship, proving that artificial sensors can seamlessly interface with biological perception. The implications of this are astounding, suggesting that future interfaces could allow humans to feel the temperature of a distant planet through a robotic rover, or physically sense the data flow within a computer network. And this is just the beginning of human augmentation. As the technology moves from clinical restoration to elective enhancement, the conversation shifts from healing the broken to upgrading the healthy. Healthy individuals might one day opt for neural implants to boost their memory capacity, download complex skills directly into their motor cortex, or interface seamlessly with artificial intelligence to solve problems that exceed natural human cognition. The biological limits of the human brain would no longer dictate the boundaries of human intelligence. This prospect of cognitive enhancement threatens to create an unprecedented societal divide. If the ability to interface directly with cloud computing becomes a purchasable upgrade, the gap between the augmented and the unaugmented could become an insurmountable chasm. We are not merely talking about a disparity in wealth or access to information, but a fundamental biological divergence in human capability. The societal transformations driven by this technology will force us to reevaluate the very foundations of equality, education, and human value. The security implications of a deeply networked mind are equally daunting. Every digital system is inherently vulnerable to exploitation, and a brain-computer interface is ultimately a node on a network. The concept of brainjacking, where malicious actors could potentially intercept neural data or even feed false sensory information directly into an implant, moves from the realm of dystopian fiction to a legitimate cybersecurity concern. Protecting the integrity of the human mind will require cryptographic safeguards far more advanced than anything we currently possess. Recognizing these existential risks, leading neuroscientists and bioethicists are urgently calling for the establishment of neurorights. These proposed legal frameworks aim to protect cognitive liberty, mental privacy, and the right to psychological continuity. The consensus among experts is that technology is advancing much faster than our regulatory structures. Establishing these fundamental human rights for the neurodigital age is critical before the commercialization of neural interfaces reaches a tipping point, ensuring that the technology serves humanity rather than subjugating it. The rapid evolution of this technology mirrors the broader history of human toolmaking, but with a critical inversion. From the invention of the wheel to the printing press and the smartphone, Humans have always built tools outside of themselves to conquer the environment. The digital pioneers had set a course that fundamentally altered our daily lives. But now, we are taking the ultimate step by bringing the tools inside, merging the creator with the creation in a profound evolutionary leap. As we integrate these technologies, we are forced to confront the reality of our own biological fragility. The human brain is a marvel of evolution, yet it operates on a few watts of power, constrained by the slow chemical transmission of neurotransmitters. Artificial intelligence, by contrast, operates at the speed of light, processing vast oceans of data in milliseconds. The brain-computer interface is the necessary adapter, allowing our slow, brilliant biological minds to keep pace with the hyper-accelerated digital world we have built. Looking further over the horizon, the perfection of these interfaces could unlock the possibility of brain-to-brain communication. If my thoughts can be translated into digital data, and that data can be transmitted and converted back into neural stimulation in your brain, the need for spoken language could eventually become obsolete. We could share raw experiences, complex emotions, and intricate concepts instantly, forming a kind of technologically mediated telepathy that would fundamentally alter human relationships and societal cohesion. This level of interconnectedness points toward a future where the concept of the isolated individual begins to fade. If millions of human minds are seamlessly connected to each other and to vast artificial intelligence networks, we may witness the emergence of a collective consciousness. The binary bridge would no longer just connect one mind to one machine, it would connect all minds to a unified digital ecosystem, creating a new form of superintelligence that is partly biological and partly synthetic. The journey of the brain-computer interface is ultimately a story about the relentless human drive to transcend limitations. We are reaching out into the dark, using the very spark of our consciousness to illuminate a new path forward. The intertwined destiny of neuroscience and engineering is not just about building better gadgets, it is about redefining the architecture of human experience. The machines we are building are becoming mirrors, reflecting our deepest desires to connect, to understand, and to evolve. As the lines between biology and technology continue to blur, we are left with a profound realization. The ultimate frontier is not out in the distant stars, but right here, within the 3 pounds of gray matter inside our skulls. We have built the bridge, and the data has begun to flow. The only question that remains is who we will become once we fully cross to the other side.